All right, welcome back, class. Today we'll talk about um, our first chapter on control charts. So this is where we will start. You will see that we will start using some of the concepts that you have learned so far in chapters 1, 2, 3, and 4, and then we start constructing our control charts. Now, as we go through this chapter, you will see that we will go through a bunch of different types of control charts. And then you might wonder, why do we have so many control charts? And this often happens the case. In fact, we are not even covering, we are just covering a very small portion of the control charts. If you open any textbook on control charts, you will see that there are plenty of control charts. In fact, there are control charts probably named after every single letters in the alphabet, from A to Z. So you can think about a bunch of different types of control charts. But what you have to be mindful is that under different assumptions and under different conditions, different control charts are developed. And that's why I like to motivate with this idea that whenever you think of a model is essentially a mathematical relationship between some inputs. Input is your X in this case, and then between the response, which is Y. So this is your input, and then this is your response. Now, uh, George Box put it very well, saying that all models are wrong, but some are useful. And this is because all models make assumptions. They don't really capture the reality. They capture the reality given some specialized conditions. So whenever we use these control charts, make sure that you read the assumptions and then the conditions very carefully before you actually use them. All right, so we'll get started with the general model for a control chart that we have already seen in chapter number 4, and then we'll go from there. So what we saw in chapter number 4 is that a general model for a control chart usually has a UCL, upper control limit, which is equal to mu of W plus Z alpha over 2 sigma of W. Center line is just mu of W, and LCL is mu of W minus Z alpha over 2 sigma of W. And then this W is your quality characteristic. Quality characteristic. Now, a couple of things here. This general model for a control chart that we're talking about, this is known as Shewhart control chart, right? Maybe I can write somewhere here. This is a general model for a Shewhart, my bad, Shewhart control chart, named after Walter Shewhart control chart, okay? And so Z alpha over 2 is a constant. And we also looked at in our previous chapter that if it's a 3 sigma control chart, Z alpha over 2 is equal to 3, right? So given that, we also looked at another thing, that whenever a process goes out of control, it can go out of control either as a result of a shift in the process mean or as a result of a shift in the process standard deviation. So whenever we develop control charts, we look at process mean and process standard deviation side by side. So the first one is you will have a control chart for monitoring shifts in process mean, right? And most of the times we'll be limited to something called an X bar chart, that again we saw a little bit of which in chapter number 4, X bar chart. And then for monitoring the shift in the process standard deviation, for monitoring shifts in process standard deviation, we'll actually use two things in this chapter. We'll use an R or a range control chart, just an R chart, and then an S chart, which is a standard deviation chart. S, which means standard deviation chart. So whenever you will see these control charts, you'll see these two control charts side by side together. Either it will be an X bar chart and R chart, or an X bar chart and an S chart. Right, so let's get started with an X bar and R chart. And then the first assumption that we'll make here is that the mean and the standard deviation of the process are known to us. And this is the same assumption that we had in chapter number 4. So given that we have some data x1, x2, ... up to xm coming from a process, sorry, xn coming from a process which is normally distributed with mean mu I, comma, variance sigma. Actually, it doesn't have to be mu I, it just have to be mu, comma, sigma squared. You can always define X bar equals to 1 over n summation of I is equal to 1 to n xi. All right, and we also know this from central limit theorem, chapter number 2, that X bar follows a normal distribution with mean mu and variance sigma squared divided by n. All right, so now what we do is we basically collect x1 bar, x2 bar, ... up to xm bar, where m represents our number of samples. Now, to give you an idea as to what exactly these x1 bar, x2 bar up to xm bar mean, think about something like an Apple Pencil that I'm using right now. So every single time I'm going to monitor my Apple Pencil, I'm going to make n measurements on every Apple Pencil. That will be denoted as x1, x2 up to xn. All right, so for every Apple Pencil, I have n measurements, and I'm going to take an average of that. That will give me x1 bar. Similarly, for the second Apple Pencil, I will compute again n measurements on this Apple Pencil, and then I will obtain x2 bar, and so on and so forth. So m represents my number of samples, and n represents number of measurements or observations. And this is also known as sample size. This denotes how many measurements you have every single sample. All right, so now that we have set up the problem, for developing a Shewhart control chart, you always need two things. You need mu of that quality characteristic. For in this instance, we're interested in X bar. So you need mu of X bar and you need sigma of X bar. If you have these two things, then you can construct a control chart. And we actually have these two things. Mu of X bar is just mu, because we just saw this result from central limit theorem, which gives us the distribution over X bar. And then sigma of X bar, this is equal to sigma divided by square root of n. Right, so now that we have mu X bar, sigma X bar, we can write down our upper control limit. This is equal to mu of X bar plus, again, I'm going to assume 3 sigma control limits unless otherwise specified. So by default, I'm assuming Z alpha over 2 equals to 3. So this is 3 sigma divided by square root of n. Your center line is mu of X bar, and then LCL, this is equal to mu of X bar plus, minus 3 sigma divided by square root of n. Now, you'll see more and more that many of the times we use constants to simplify some of these formulas. So in this case, we actually use a constant called uppercase A. We basically end up with mu plus A sigma. This is equal to mu, and then this is equal to mu minus A sigma, where A is equal to 3 over square root of n. So let me mark this up. This is your first control chart, X bar control chart. And this uses a constant A 3 over square root of n. And as we develop more and more control charts, you'll see more and more of these constants. But all of these constants are actually given in appendix 6 of your book. And even in the exam, I will provide you with this appendix, so you don't have to worry about having this appendix with you. All right, so now let's get back to so we have talked about X bar chart. Now let's talk about R chart. R chart, as the name says, range. R stands for range. So let's say you have data x1, x2 up to ... up to xn. Again, n measurements on every single Apple Pencil. You would compute range of these measurements. This will give you, this is equal to maximum minus minimum. And then this is what we denote as range R. Now, again, if you have to develop a control chart if you have to develop an R control chart, you need two things. You need mu of R and you need sigma of R. Now, we don't have any central limit theorem, just like X bar, but we do have some statistical results that people have obtained a long time ago that talks about the distribution of the range. And then the distribution of range, from the distribution of range, we can derive the mean of the range and standard deviation of the range. Mean of the range is given as d2 times sigma, and the standard deviation of the range is given as d3 times sigma. Both d2 and d3 are constants. So let me write this down. d2 and d3 are constants. And again, these are available in that same appendix 6. When we do a problem, you will see how we can use appendix 6 to estimate the values of d2 and d3. Now that you have mu of R and sigma of R, we can write down UCL. This is equal to mu of R, which is d2 times sigma, plus z alpha over 2 is 3 times sigma of R, which is d3 times sigma. Center line is d2 times sigma. Lower control limit is d2 times sigma minus 3d3 sigma. You can do some simplification here. You can say this is sigma times d2 plus 3d3. This is sigma times d2. This is sigma times d2 minus 3d3. And now I can take this term inside the parenthesis as uppercase d2. Central line remains as sigma times lowercase d2, and then LCL becomes sigma times uppercase d1. Again, these constants are available in that same table. So all you need to know is sigma and the sample size, which is little n. If you know these two things, you can estimate d1, uppercase d2, and lowercase d2. All right. So this was the X bar control chart and R control chart under the assumption that mean and standard deviation are known to us. Let me write this down. This is the R chart. This is the X bar control chart. Okay, when this assumption is not satisfied, in other words, when mu and sigma are unknown, what we do typically is we estimate some of these parameters, for instance, the mean and the standard deviation and the range from data itself, right? Now, for the purpose of this course, you don't have to work directly with data. Maybe in some of the assignment problems, I might ask you to use data to estimate some of these values. But for the exam purposes, you will not be asked to compute these statistics like mean and standard deviation and range from the data, because it's very time consuming. But I still want you to give you a flavor of what it truly means to extract some of these statistics from data. So for instance, if you're working on a real life problem, you actually work with data, and then from that data, you derive some of these statistics. So typically, the data would look something like this. You have index here, and let's say index basically represents all of your samples, which can go from 1 to a dot 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 up to m. So this represents samples. And always remember, m for the entire course represents the number of samples. So think about the number of Apple pencils that I'm going to be investigating or monitoring. And then for every single sample, we are going to collect some measurements. These measurements or observations are across the x-axis. So 1, 2, 3, dot, 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 up to n. These are our observations. And n is our sample size. So for every Apple pencil, this is how many measurements we are going to make. And then you have x11, x12, x13, dot, 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 up to x1n. And now from the data, you can compute x bar for every single sample average. And then for every single sample, you can also compute its range, which is r. This will lead you to x1 bar, which is equal to summation of xij. J goes from 1 to n divided by n. Similarly, you have x2 bar, dot, 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 up to xm bar. And for range, you have r1, r2, dot, 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 up to rm. And then finally, we'll compute the grand average and then the overall range. So the grand average is x double bar, which is 1 over m summation of xi bar. I is equal to 1 to m. And then r bar, this is equal to summation of ri. I is equal to 1 to m divided by m. And then now you have x double bar and r bar. Now let's actually go back to the control chart. So in this scenario, we still want to construct an x bar and r control chart, but we don't know mu and sigma. So if we don't know mu and sigma, we're going to estimate them from data. Okay, so let's first talk about x bar control chart. For x bar control chart, we need mu of x bar and we need sigma of x bar. Mu of x bar, we can estimate. This is generally mu, right? But we don't know mu. And sigma of x bar is sigma divided by square root of n, but we don't know sigma. So what we're going to do here is we're going to estimate. Again, we can refer to chapter number 3 where we talked about different types of estimators. So we estimate mu using x double bar. So we'll say mu hat is equal to x double bar. And then plugging back into the formula, we get mu of x bar hat. This is equal to x double bar. Similarly, we will estimate sigma using range r bar. And then the formula that is used to estimate sigma with range is r bar divided by d2. And so now I can plug in sigma hat in my original formula for sigma x bar, and I get sigma x bar hat. This is equal to r bar divided by d2 square root of n. Well, now I have mu x bar and sigma x bar, they're estimates. So that's why we have this hat symbol. Now I can go back and construct my x bar and r control charts. So returning, you have UCL equals to mu of x bar plus 3 sigma of x bar, which is equal to x double bar plus 3 r bar divided by d2 times square root of n. Center line is mu of x bar, which is x double bar, simply x double bar, and LCL is mu of x bar minus 3 sigma x bar, which is x double bar minus 3 r bar divided by d2 over square root of n. And again, we can do some simplification here. We can write the UCL as x double bar plus a2 times r bar. Central line is already simplified. LCL is X double bar minus A2 times R bar, where A2 is equal to 3 divided by D2 square root of n. So you see, now if you know n, you can automatically compute A2, right? Again, A2 is available in the in your appendix 6. So this is your X bar control chart for unknown mu and sigma. Okay, so we have done one part of it. Now we have to go and talk about our control chart. So our control chart, for our control chart, again, we need two things. We need mu of R and we need sigma of R. What we know about mu of R is it is D2 times sigma, and sigma of R is D3 times sigma. So all we have to do is to estimate sigma, and we already have an estimate of sigma. We just did it a while ago. So we estimate sigma using this equation. Sigma hat is equal to R bar divided by D2. So now plug this sigma back into mu of R. This will give us mu R hat. This is equal to R bar divided by D2 times D2, which is just R bar. And then sigma R hat, this is equal to D3 times sigma, which is R bar divided by D2. So now you see we have sigma mu of R hat, and then we have sigma R hat. And now I can return and compute my R control chart. So your UCL, I'll just give you the final formula. This is equal to R bar plus 3D3 divided by D2 times R bar. CL is R bar and LCL is R bar minus 3D3 divided by D2 R bar. We can simplify the numerator by writing it as 1 plus 3D3 divided by D2, and this constant inside the parenthesis is D4, uppercase D4. Your center line is still just R bar. Your lower control limit is R bar times 1 minus 3D3 divided by D2, which is R bar times D3. Right? And so now you have your, this is your R control chart for unknown mu and sigma. All right, now let's look at some problems that we can solve using these formulas. The first problem is we wish to establish statistical control of the flow rate of the resist. Resist is a type of a polymer using X bar and R charts, 25 samples, each of size 5 wafers. So you see your M is 25 because you have 25 samples, and then each sample is of size 5. So your N is equal to 5. The interval of time between samples of subgroups is 1 hour. It's probably not a useful information at this point. But if you actually look at the data looks something like this. On the first column, we have sample number that goes from 1, 2, 3, 4, 5 till 25. So dot, dot, dot. And then for each sample, you have 5 measurements. 5 wafers, measurements on 5 different wafers. So now you can compute X bar and range for every single sample. Again, you don't have to do this for the purpose of this course. We have already given you these numbers, and all you have to do is to use these numbers to compute, to answer the question. So in this case, we're constructing an X bar and R chart, and you can see here that we already have estimated X double bar and R bar from the data. Right? And then once you have X double bar and R bar, your X bar control chart, X bar control chart looks something like this. The UCL is X double bar plus A2 times R bar. This is equal to 1.5056 plus we have to look at A2. So A2 depends on the sample size n. N is 5. So if you look at this appendix 6, this is again appendix 6. Let me go back to the clearer version. So this is appendix 6, and you can actually see here on the second column, we have A2 right here. We're interested in n equals to 5. So your estimate of A2 is 0.577. All right, so let's go back and plug this in. Plus 0.577 times R bar, which is 0.3252, which will give you 1.6932. Your CL is just X double bar, which is equal to 1.5056. And then your LCL, this is X double bar minus A2 times R bar. This will give you 1.3179. Right? You can fill up the blank here. 1.5056 minus 0.577 times 0.3252. That's your control chart. And similarly, we can construct our R control chart, which is UCL is D4 times R bar. Again, let's look at D4 in that appendix 6. D4 is the very last column. So for n equals to 5, we have 2.114. So let's plug this in here. This is equal to 2.114 times R bar is 0.3252, which gives us 0.6875. R bar is simply 0.3252, and D3 is 0. So your LCL is just 0. This should be subscript here, not as a multiple. Okay, so that's how you would construct XBAR and R control chart. Now, many times, we use the softwares that are available that can be used very easily to construct these control charts. And one of these softwares is called a JMP. What my plan is to have like a small short lecture, record and upload on how to use JMP for doing some of these things. And maybe I'll do that once we finish chapter number 6. So somewhere close to chapter number 6, I'll talk about the JMP exercise. But yeah, in this case, you can actually see that we just developed the control chart for the same example that we have just did. And yeah, sample 7 is not out of control. This is a typo here. So let me take this off. And constructing control charts is fairly straightforward. So I'm not going to spend a lot of time on that. What I want to spend some time on explaining to you is phase 1 and phase 2 control charts. Now, phase 1 of developing a control chart is a process when you are trying to set up the control charts. You're not monitoring the process using the control charts. So phase 1 monitoring, we call it monitoring, but really this is where you set up the control chart. So I'm going to say setting up control charts. Think about setting up the control chart as a process when you truly certify your process. You truly understand what is the real variability in the process and when a process is truly in control, right? So your whole objective in this case is to make sure that the process stays in control, right? Make sure the process run as ideally as possible. And when you're constructing these control charts, for some reason, if you encounter a sample outside the control limits, the idea is to remove them. You remove them and then you redo the control chart. Right? You have to make sure that when you are in phase 1, there are no out of control situations that we're calling here as outliers. If you see any outliers, remove the outliers, and then you re-estimate your X double bar, R bar, and S bar, and then you again construct the control limits. It's a phase 2, make sure that the process is in control. Let me make sure here, let me write this down. Make sure the process is in control, right? Okay, so now you have certified your process. Now you know what are the true upper control limits and lower control limits. Now, once phase one is done, once you have established the control limits, you do not you do not touch the control limits. Control limits stays fixed. And this is when you start phase two of the process, where you start monitoring the process using the control charts. Now you'll start seeing out of control, in control. And so whenever there is an out of control situation, you might sound an alarm, or you might wait and see whether this is a false alarm or this is truly an out of control situation. So this is where you really start using the control chart. So that's the distinction between phase one and phase two. And I have given some problems in the assignment as well to walk you through how to construct phase one and phase two. Okay, fantastic. And actually, I gave an example here. So using the same control charts, we first established the upper control limit and then the lower control limit that you see here. And the green points are our phase one, the data from our phase one part. So this is, let me use a blue color. This is phase one monitoring. This is where we have constructed our control charts. Once we constructed our control charts, now then we are observing future data points, which are denoted in black color. And then you clearly see that there is an upward shift in the data, indicating that there's something wrong. And then towards the end, you see that the measurements are outside the control limits, indicating that the process is going out of control. And when I upload that lecture on JMP, you will see how we can use this type of a data to construct a control chart. All right, now let's look at one more problem. This is more of a representative problem that you should truly understand how to solve, because as a quality control engineer, your job is not really to construct the control chart. Control charts could be constructed using different softwares. Your job is to really use the control chart and make inferences similar to what we're going to do in this problem. So the problem says an XBAR control chart is used to control the mean of a normally distributed quality characteristic. It is known that sigma is equal to 6, n is equal to 4. Center line is 200, UCL is 209, LCL is 191. So you already know the control limits. If the process mean shifts to 188, find the probability that this shift is detected on the first subsequent sample. Right? So this is the type of question that you should be able to answer as a quality engineer. So in this case, we're interested in answering the probability of detecting the shift on the first subsequent sample, given the process is out of control. The process has already gone out of control, right? Okay, so probability of detecting a shift can only be detected if a measurement falls outside the control limits. So this is basically saying probability X bar is greater than UCL or it is less than LCL, given the process is out of control. And we already know our UCL and LCL, but we probably might not need it here. You can still use it, but we might not need it. We can rewrite this as 1 minus probability X bar is less than equal to UCL greater than equal to LCL given OOC. This might appear a little bit familiar. This is the type 2 error that we have already computed. So this second term right here is the type 2 error beta. So I can write this as 1 minus beta. And now if I can compute beta, I can figure out this probability. Beta, this is equal to phi of Z alpha over 2 minus delta square root of n divided by sigma minus phi of negative Z alpha over 2 negative delta divided by n times square root of n divided by sigma. Delta in this case is, let's see, your in control process mean is your center line. Center line is 200. That's your in control process mean. And then the process mean shifts to 188. So there's a shift of 12 units. So I can say delta is 12. Question does not say anything about the value of z alpha over 2, but I'm going to assume for simplicity right now that z alpha over 2 is 3. Z alpha over 2 is 3. So now I also know sigma. Sigma is 6 and n is equal to 4. So I can compute beta equals to phi of 3 minus 12 square root of 4 divided by 6 minus phi negative 3 negative 4. This is equal. So if you compute this, you'll get 0.1587. And so plugging this back in, you get the final answer as roughly 0.84. Right? So there's 84% chance of detecting the shift from 200 to 188 on the first subsequent sample, which is not bad, which is truly a good performance of a control chart. It also says calculate the ARL1 for the process. ARL1 is simply 1 over 1 minus beta, and this will give you roughly 1.19, which is again good because it says if the process goes out of control, you have to roughly wait on an average for maybe just around one sample or 1.19 sample. Now, what I want to do here quickly is I want to change the value of n. So right now, we just saw that n equals to 4, delta equals to 12. This leads to a beta of 0.1587, type 1 error of 0.1587. I want to see what happens when n is equal to 9. Now I've increased my sample size. For example, in terms of Apple Pencil, instead of taking 4 measurements on one Apple Pencil, I'm going to be making 9 measurements on every single Apple Pencil. So now in this case, beta is using the same formula, phi of 3 minus delta is 12 square root of n, which is 9, divided by sigma, which is 6, minus phi of negative 3, negative 6, which is roughly 0.0013. So you see now, by changing from n equals to 4 to n equals to 9, there's a dramatic reduction in type 2 error. In fact, you will also see that ARL1 has reduced. This is equal to 1 over 1 minus 0.0013, which is roughly 1.001. So this indicates something very powerful about control charts. And let me try to summarize that. Point number 1 is if delta or absolute value of delta and alpha are fixed, then type 2 error or beta decreases as n increases. And this is a powerful result because let's say you are concerned with improving the performance of your control chart. In other words, decreasing the type 2 error of your control chart. One way of doing this is by increasing the sample size. Now, this does come with a clause. If you increase sample size, there are some limitations because if you increase n, you have to increase the number of samples. And if you think about it, collecting samples is costly because you will have to invest resources and time. So you can't always continue to increase the sample size. There's a limit, there is a budget constraint, there's a time constraint to it. But there's one more thing. Number 2 is if alpha and n are fixed, beta decreases with increase in the magnitude of shift. Now, this might appear a little bit intuitive. If there is a larger shift in the mean of the process, then it's easy to detect that shift. Even visually, we can see and identify that there has been a shift. And so if it is easier to detect the shift, type 2 error is usually very, very small, or probability decreases as it becomes easier and easier to detect the shift. All right. So these are the two important properties that I would want you to remember about control charts. And these two properties are very nicely captured in this curve called operating characteristic curve. On the x-axis, this actually gives you value of D, which is absolute value of delta divided by sigma. Sigma is constant. Y-axis is your type 2 error or beta. And you can see here that if you fix n, if n is fixed here, as the value of delta increases, type 2 error decreases because we basically track this path, right? As we move to the right, you see your type 2 error decreases, your delta increases. And similarly, if you fixate on this dotted line that I have drawn here, your delta is fixed, your n goes from 1, 2, 3, 4, 5, 6, 7, all the way to roughly 20. And you see that as the value of n increases, as the sample size becomes larger, type 2 error decreases. So make sure that you remember these two properties, very important about control charts and very useful in understanding how we can improve the performance of a control chart. All right, let me stop here and I'll see you next time. Thank you.